Okay, so this video is going to be on the idea of graphing and writing equations of absolute value functions. So, a couple things we need to know are the basic definitions. So in this particular video, what we have here is we're going to be graphing functions that are based upon the absolute value. So we're going to be just graphing other ones, but this is kind of the important piece that you understand, that we're graphing off of this function. So there's a basic definition to the absolute value. So the absolute value is actually a function. It's actually telling you what to do. It's actually telling you what to do based upon the value that you use for x. So if I use a value of x, so let's go over to here. So if I use a value of x and that value of x is greater than or equal to 0, my answer will be just that value of x. Whereas the next time, right, I have another thing here that says, okay, if I have a value of x that is less than 0, i.e. a negative value, to get my answer from the absolute value, I must multiply that value times -1. So just to demonstrate this very quickly so that you understand the absolute value and how the answer works, it's not just this thing where, your teacher always tells you the absolute value is just positive. There's a reason that it's positive, and it's because the absolute value is a function. It's a standard rule based upon restrictions on our domain. So, for instance, if I take a number that's negative, so say I take a number like -2, and I look at that value and I evaluate it. I'm supposed to do something yet. So to calculate my function, my output, so I'm using function notation here to calculate what the value of f of x would be. The value of f of x is found by evaluating the absolute value of that number. So if I go into here, I have -2, I go up here and I follow the path over and I say, okay, I chose a number that was less than 0. So therefore, my answer is just found by taking that value of x and multiplying it by -1. So -2 times -1 is inevitably the value of 2. So that's why when your teacher tells you that the absolute value of -2 is 2, it's simply because any negative value, you simply multiply it by -1. So again, if we continue this table, we get -1. And if we go back up to where we were, we take it because we chose a negative, so we go to the interval, all right, where the value of x is negative. So this value that I'm choosing is less than 0, so I will take that value and multiply it by -1, and what you get is now +1. So now let's take a look at the next one. So I'm progressively going towards 0. So 0, so I pick up the number of 0, I plug it in. So 0 this time, notice I go to the value where it says equal to 0. So the absolute value of 0, right, is going to be just 0. So you can take that number as it is and you get 0. Now, if I start going into the positives, right, a number greater than 0 is 1. So 1, I go again back up to my function and I realize I chose a number greater than 0, so I can just use that number as its output. So an input of 1 corresponds to an output directly of itself, which is 1. So again, if I continue on this, I get 2 and 2, and what you begin to build is the bare basics of what we call the parent function. So the absolute value is the bare basic bones. So what we call this right up here is called the parent function. The reason it's called the parent function is because it is dealing with an operation based upon no other operations, meaning this function is being evaluated with absolutely no other operations. There's no additions, there's no subtractions, there's nothing like that going on, there's no multiplications, there's no divisions. So that's why it's called the parent function. It's just using the function based off of one value. So we need to use this for later on in the video. So we're going to jump to graphing these with transference. So again, what we're going to do is we're going to take a look at this and we're going to say, okay, g of x equals x plus 1, the absolute value of x plus 1 minus 3. So we're going to base this function, okay, graphing it, off of our f of x. Okay, our f of x equaling the absolute value of x, okay? So when we use these values, there's a couple things that I want to talk about. So I'm going to make this table like we had before, all right? And one column will be called f of x, and another column will be called g of x. So we have 2 columns going in here, okay? So column 1, column 2, here comes column 2 now. Column 1, column 2, and we're going to base that off of the top here. So we have this, and we go like such. All right, so I'm going to make a nice neat table here, and this table is going to be the same values of x, okay? So I'm going to take the value of x, and I'm going to take a look at something. So the value of x that I'm going to use is still going to be negative 2. It's going to be negative 1. It's going to be 0. It's going to be 1. And it's going to be 2. So now, if I take this and I start evaluating it, remember if we did f of x, okay, f of x was just the value. So if it was less than 0, we just multiplied it by negative 1. So f of x is going to be taking negative 2 and multiplying it by negative 1. So negative 2 times negative 1 is going to be the output of 2. Negative 1 times negative 1 is 1, 0. And if it was 0 or greater, we just use that number as was. So the absolute value of 0 is 0. And the absolute value of 1 is 1. And the absolute value of 2 was just 2. So now let's take a look at what do we get for when we plot g of x, okay? So when we plot g of x, all right, we're going to use the negative 2. So I'm going to plug negative 2 into the function for g of x. So what I get is the absolute value of, and this is what I'm going to do in my work. I'm going to show it for the first one, but then I'm going to just do mental math along the way. So negative 2 plus 1, and then I'm going to subtract 3. So the absolute value of negative 2 plus 1. So the absolute value of negative 2 plus 1 is negative 1. And the absolute value of negative 1, so I get that this is the absolute value of negative 1 minus 3. And we already learned that if the value inside the absolute value is negative, we must multiply it by negative 1. So negative 1 times negative 1 is 1, and 1 minus 3 equals negative 2. So the answer to g of x for this one is going to correspond to end up being negative 2. So I'm going to erase all my work here, and I'm just going to place a negative 2 in here. Okay, now let's do the same thing. We're just going to plug negative 1 in. So when I plug negative 1 in, all right, I get 0. So the absolute value of 0 is 0, and 0 minus 3 ends up being negative 3. And then I take a look again. So I go to 0, plug 0 in. 0 plus 1 is 1. The absolute value of 1 is 1, and 1 minus 3 is negative 2. And then I go on likewise, and I just continue this on. I go 1, plug 1 in. 1 plus 1 is the absolute value of 2. And the absolute value of 2 is 2. And 2 minus 3 is negative 1. And then I go on to 2. So 2 plus 1 is, 2 plus 1 is 3. The absolute value of 3 is 3. And 3 minus 3 is 0. So all I did there was I did some mental math, but I showed the steps above. So the second time I did the mental math, all right? Now, what I'm going to do is I'm going to plot both the graph of f of x and the graph of g of x. I will plot the graph of f of x in black, and I will plot the graph of g of x in blue. So we're going to then take a look at what does the graph look like, and how can I begin to just graph these things, okay? And what can I determine, what do these values do, and how can I use them, okay? So for this value, I plot the graph of f of x, and the graph of f of x is just these points. So negative 2, 2. So I go over 2, up 2. I go over 1, up 1. So plot the point negative 1, 1, plot the point 0, 0, plot the point 1, 1, plot that point there. And then I have a graph. So I'm going to go ahead and graph this. Okay, as best as I can. So the graph begins to look like that. Okay, so what you have is this V shape, all right, going on. Now, we want to take a look at g of x, okay? We want to plot its points. So now we plot the point of negative 2, okay? And then we're going to plot the point negative 1, negative 3, so negative 1, negative 3. And then we plot the point 0, negative 2. And then we're going to plot the point 1, negative 1. And then we're going to plot the point 2, 0. So in blue, I plotted my same x-coordinate as before, but then I plotted with it this third column, okay? So what you begin to notice here is I get the same looking V shape, okay, as I had before. The only difference is what happened here. Like, what's everything doing? So it looks like, right, so we have this graph. What ends up happening is that point of positive 1, negative 3 is interesting. Because if I go look at what we call the lowest point of this function, which is called its vertex down here, okay, so the lowest point here of an absolute value, or the highest point of that value, okay, it's just the point where the two rays meet, is called the vertex. And the value of that vertex is the point, actually, negative 1, comma, negative 3. So what ends up happening is we make a correlation here that this point, the original vertex of the original function, then mapped to here. So when I did some alterations to it with addition and subtraction, it ended up looking like it moved my graph over to the left and then down 3. And if you notice that I go to every point that corresponds with one another, so a word out of geometry is the same position, it goes over 1 and then it also goes down 3. And again, over 1 and down 3. So if I take this point that corresponds up here, I go over 1 and down 3, over 1, down 3. So every point here is moving in unison. They're all going over 1, down 3 points, over 1, down 3 points, okay? So I look at all of my graphs and I take all of their information, they're all going left 1 and then down 3. So these are all following, if you see here, me drawing them, they're all following the same pattern. So what I begin to recognize here is that this plus 1 up at the top in the original function, if we take a look at that g of x up top here, it looks like this positive 1 is actually causing my graph to move left, but when outside the function, it actually is mapping directly to it. So this is a direct mapping, and this is what we call a reverse mapping, or an opposite mapping, meaning if I add 1, it's actually causing my function to move 1 to the left. Okay, so that's an important piece. So this is what we call a translation. So in the absolute value function, all right, based upon the parent function, based upon their original points, okay, if I add 1 on the inside and then subtract 1 and take a look at its new mapping, the graph seems to be moving, okay, when I take a look at the coordinate pairs, compared the input to the output, if I add 1 to the function's original input, and I take away 3 to the function's original to that function's output, I then get a graph that ends up looking like it was shifting 1 left and down 3, 1 left, down 3. And because every point is moving in unison, all right, this is what we call a translation. It's just simply a shifting of the graph. So this graph was shifted, okay, or translated, if you want to use the proper word, it was shifted 1 unit left and 3 units down. Okay, so this is going to be an interesting concept that we have to kind of follow, and let's take a look at the next example and see, does this always work? Let's see how it works. So on to the next example. Now, this example says 2 times the absolute value of x minus 10 plus 4. So let's take a look at what everything has here. But for this one, I'm gonna actually get rid of the 2 so that you can kind of see it a little bit better. So we're going to start off with the absolute value of x minus 10 plus 4. So if I were to take a look at this function, right, and I were to say, okay, let's take a look at f of x compared to h of x. So I'm going to have some values of x, and I'm going to plug them into my table. Okay, so I'm going to make a table again. So here goes my table. So if I use the same values, just keeping still with them, -2, -1, and then I use 0, 1, and 2, all right, and then I take a look at what would f of x be, okay, and f of x, remember back to the first slide there, is just going to be the absolute value of x. So I'm going to write that above. So that's what we call the parent function. So f of x for all of these things will always be the parent function. And then h of x is going to be what is the new output, okay? So based upon the previous slide, what we noticed is that when I had the value on the inside that was positive, right, it seemed like it shifted it to the left. So I'm going to hypothesize right now that since this is a minus 10, I'm thinking this is going to move as the opposite of what it says. So I'm thinking maybe that this moves actually to the right 10, and the plus 4, well, the last one said minus 3, so I'm just going to take a quick little guess and say maybe this goes up 4. And if that works, all right, I can then make a generalization, all right? So let's just check if this works, and then I'm going to make a generalization about this. So here we go. Again, so we're going to go back to the f of x. So the f of x we're going to fill in very quickly because it's just the absolute value of -2. The absolute value is 2, -1. The absolute value produces 1, 0, 0, 1, 1, and 2, 2. So now let's go to h of x. So h of x is going to be, I'm just taking this value of x and I'm plugging it in up to the function up top. So again, just so you see that, I'm taking the value of this x column and I'm plugging it in up here, and then I'm going to map its new coordinates, and then I'm just going to take a look at what happens. So -2 minus 10 is -12, and -12 okay, the absolute value of negative 12. So I'm taking a look at the absolute value of negative 12, which is 12. Okay, and then I'm going to add 4 to that, which produces 16. Okay, wonderful. Got it. So then I go to negative 1. So absolute value of negative 1 minus 10 is negative 11. The absolute value of negative 11 is 11, and 11 plus 4 is 15. And then I'm going to take it 0 and plug 0 in. So when I go ahead and I plug 0 in, okay, I take a look at this and I get, awesome, I get the idea of taking 0 minus 10, which is negative 10. The absolute value of negative 10 is 10, and 10 plus 4 is 14. So let's plug a 1 in. So 1, so we take a look at this, right, and we go 1, all right, 1 minus 10 is negative 9. Absolute value of negative 9 is 9. So 9 plus 4 is 13. So again, now I'm starting to establish a pattern here. I go 16, 15, 14, 13, right? So what I'm going to do here is I'm going to continue this pattern. I'm just going to take a wild guess that this is going to be 12. So let's just double check it. 2 minus 10 is negative 8. Absolute value of negative 8 is 8, and 8 plus 4, okay, 8. Now we have 8 plus 4 is 12. Good, so it's 12. Now, I see that this number is trending down towards 0. So what number would make my answer become a 0 here? So let's just go down and see how far we have to go to make this work. And I'm going to go all the way up to the value of, I believe what I would think is going to be a value of 10. So I'm just going to plug a 10 in here. And the reason I'm plugging 10 is so that I can get my absolute value to be the absolute value of 0. And then I'm going to plug 11 in, okay? Because up to this point, I've gotten, every time I plug those numbers in, I've gotten an absolute value of a number that was actually going to be a negative. So I'm thinking to make the outcome of this number to be positive, that x has to be a number greater than 10. So I'm going to use 10 as my base, as my 0, and then if I choose a number beyond 10, then that answer should be positive. So if I plug 10 in, I get the absolute value of 10 is, minus 10 is 0, and 0 plus 4 is 4. Okay, so if we took, so this right here is 4, okay? So let's just take a look at what the absolute value of f of x would be at 10, and that would be 10, okay, just so we have a reference. And f of x for 11 would be 11, so I'm just filling in the parent function here just so we have something to compare it to. So now I plug 11 in. So the absolute value into h of x, okay, which would be the second function up here, the one we're trying to graph. So 11 minus 10 is going to be 1. The absolute value of 1 is 1, and 1 plus 4 is 5. Okay, so this thing seems to now, it was trending down, and it hits a low value of 4, and then it starts trending back up. So when I got to that positive number, notice what happened. I was trending all the way down, and I couldn't get below 4. Well, that kind of makes sense to me right now, but let's just take a look at the graph. That's the thing that we're kind of doing here. So let's take a look and plot this graph. So f of x, we go ahead and plot that in. I'm just going to do it kind of quickly here. Okay, so f of x is in black here. And then we're going to go ahead and we're going to plot into here h of x. So h of x is going to be, in this time, we'll make h of x green. So h of x is green. I'm just going to plot the points. So if I plot the point, negative 2, 16, I can't plot it. It's not on my graph. So I'm going to plot negative 1, 15. So negative 1, 15, here's that point. And then I'm going to plot 0, and I get 14. So here's 0, 14. And I plot 1, so the value of 1, I get 13. Plot 2, I get 12. And then I skipped to the value of 10, and when I plotted the value of 10, I got 4. And then when I plot the value of 11, I got 5, so it started going back up again, which makes sense to me because the absolute value is going to go down to one point and then start going back up. So if I go ahead and I graph this, okay, there's my function. Okay, there's some things that I want to take a look at here. And a couple of things I want to take a look at are this coordinate versus this coordinate. So these two are vertexes. And the coordinates of the original vertex is 0, 0. And the vertex of the new coordinate is, looking at this, is 10, comma, 4. So what's interesting here, again, is we kind of get this reverse effect going on. Remember in the previous video, our vertex went when the inside was add 1, we went left 1, and then we went down 1. Now, all of a sudden, if I take a look at this video, when I'm subtracting 10, my hypothesis ends up coming true. This point ends up going to the right 10, and then on the outside, I say, remember, plus 4, that it would go up 4. So every point on this original function is just being moved, and they're all being moved the same. So if I take a look at this function here, and I take a look at them all, right? And I say, okay, how are they being moved? Well, they're all being moved, okay, over to the right 10, and then they're being moved up 4. So if I take the point negative 1, 1, and I go over 10, that gets me at the value 9, and then I go up 4, it gets me the coordinate now of 9, 5. So I went from, in this particular case, I go from the value of negative 1, 1 to the value of 9, 5. Well, if you take negative 1 and add 10 to it, it makes 9. And if you add 4 to 1, it makes 5. So what's happening here is every point, again, is now, again, moving in unison of over 10, up 4, over 10, up 4. So what's ironically happening is that these numbers are actually giving me direction as to how I can move all of my points. So for this one, I think what's important is that we begin to notice is that all of my points are simply moving, okay, all in unison. So if I want to graph a transformation, it's going to be very, very important that I recognize the starting point known as what we call the vertex. So if I move the vertex over, okay, so from there I can just simply begin to graph the absolute value function as I would based upon its vertex. And all of the absolute value functions, when I take a look at this based off the absolute value function, okay, if they follow the absolute value rule. So the absolute value rule is if I move 1 to the right, the outcome tells me to go up 1. If I move to the right 2, the absolute value function also tells me to go up 2. So over 1, up 2. Plug in a value of x, I go up to the value of 2. And then converse with that, okay, if I go over 1, I also go up 1. If I go over 2, I also go up 2. So notice I'm having a direct mapping. For the amount that I go over, I go up that amount. So how can that happen here? So if I begin to just move this original point over the 10 and up to 4 to get the original, I can then take a look at what's happening here is if I have a function that just has a subtraction or addition in here, okay, I'm noticing that inside the function, my graph ends up moving the opposite way of what this sign is. However, it's moving the direct way that this sign points. So I think that's a good rule to go by. I think that's what we should go by. I think we should go by you do the opposite of what's on the inside, and you will do the exact of what you see on the outside. So now, how do I get the final graph of this thing here in green? Well, I'm just going to follow what I do from the vertex of the original function. The original function says go over 1, up 1. So that's what I'm going to do. Over 2, up 2. And notice I'm landing right back on the line. Over 3, up 3. Over 4, up 4. Over left 1, up 1. Left 2, up 2. Left 3, up 3. And that's nice to have because now I have a general rule that if the interior is adding or subtracting, okay, I do the opposite. So I will move my vertex the opposite of the interior, and I will move the y coordinate, okay, the output, I will then change it by doing directly what it says to do on the outside. So now that our rule's established, let's take a look at a more complicated one. So for this one, we have a different scenario going on. A different scenario we now have going on is the fact that I am now putting this multiplier of negative 1/2 out front. So let's take a look at again what happens when we do that. Let's do the same thing, but instead of this time, instead of making a table like we did before, I'm going to use our rules here. So our rules here say, okay, the vertex should go opposite of this, which is left 5, but yet the same as this, so up 2. So the original function is going to be important that we know where does the original f of x function start. And I'm going to go ahead and graph that again in black on the screen here to keep this kind of going. Okay, so here it is. There's the original parent function. Okay, so we now have that parent function. So remember, the operators on the inside, that addition sign, told me that normally, okay, I would take my point, so I'm going to use the vertex here, and I'm going to take that point now, and I'm going to move it left 5 and up 2. So left 5 and up 2 and plot the point. So there's my new vertex, okay? So now normally, all right, I would just go ahead and plot this, and I would say, okay, well, we can't ignore this -1/2 though, okay? So I can't just sit here and start to go plotting and following the rules. So what does this -1/2 end up doing? So let's take a look at, based off of the value of x starting at -5, that's where my new vertex is, let's make a little table and let's see what happens when I use this -1/2 in the order of operations to make a quick little table out of this. So make a quick little table, and we're going to surround it around the idea, again, of this -5 as being our vertex. So now I'm going to use points that are around my vertex, and I just want to see kind of what happens and what does this -1/2 do when I apply the order of operations to it. So x. So the x I'm going to use is going to be, the x values I'm going to use are going to be to the, around this -5. So I'm going to use 2 values to the left of -5, maybe 3 values. And I'm also going to use 2 values to the right of -5. So I'm going to use the values of -7, -6, and then I'm going to use my -5. And then I'm also going to use the value of -4 and -3. So those are the values I'm going to plug in. And I want to see what happens. What do I create? Because if I can make a general rule right now about, I've kind of got what the inside is doing, and I'm just going to make sure and find out, I'm going to check out what does this -1/2 do. So here we go. Let's take a look at it. So all I'm going to do is I'm going to plug these values in, -7. So just to show some side work, just so you understand, I'll show it for the first one, but then I'm going to do mental math for the rest, okay? So I'm going to do -1/2, okay? Absolute value of -7 plus 5, and then plus 2. So again, so I'm going to do -1/2, absolute value of, so this is times the absolute value of -7 plus 5 is -2, plus 2. And then remember, the original parent function said if I get a negative value inside my absolute value when simplified, that I will just simply multiply that value by -1. So I now get -1/2, and -2 times -1 is 2. So I'm now doing 1/2 times 2, and then I'm going to add 2 to it. Okay, so all of this mental math, so -1/2 times 2 will be -1, and -1 plus 2 has a final outcome of the number value of 1. So what I'm going to do is I'm going to erase all of this work now. I'm going to do mental math, but up here, what you see is all I'm doing is plugging numbers in and doing the order of operations. So g of x in this case went from, when I plugged in -7, I got an output that was +1. So in this case, I'm just going to write a 1 now for g of x. And then we're going to take a guess at, you know, kind of what does this do, okay, for the rest of my functions here. And then we'll go from there. So what we have here, okay, just so we're all aware, is I'm just simply plugging stuff in. So what I'm now going to do, all right, is I'm going to do this, but I'm going to do this with a -6, and I'm just going to do some mental math with this, okay? So if I plug a -6 in, I get the absolute value of -1, and that becomes +1. So -1/2 times 1 is -1/2, and -1/2 then plus 2, okay, -1/2 plus 2 then ends up being 1.5, okay? So let's see what happens when I plug in -5. So if I plug in -5, okay, what I get here is I get -5 plus 5 is 0. The absolute value of 0 is 0. So 0 times -1/2 is 0. And then 0 plus 2 is 2. Which is kind of cool because this value right here, okay, when I move the vertex, notice what I end up getting the value that I said I was going to get, which is kind of nice that that happened, okay? So even having this multiplier out front here, it doesn't change the fact that the values on the inside here are still moving the vertex directly to where they're supposed to be. You just need to remember that this operator on the inside, this positive or subtraction, moves it actually the opposite way when we plot the points and plug it in than it does versus the outside, where the outside moves it directly. So if you notice, the vertex went left 5 when it said plus 5, but it definitely went up 2 even when it was plus 2. So interior, again, opposite movement, and then this one is just move it directly the way it is. So now let's check -4. So I take -4. I'm going to plug -4 in. And based off of absolute value, I do know what the answer should already be, but let's just go ahead and do this. So if I plug the -4 in, -4, I get +1. The absolute value of +1 is 1. 1 times -1/2 is -1/2, and -1/2 plus 2 ends up being, again, this value of 1.5. So, which is nice because now I have what we call some symmetry going on. And let's just check -3. So when I plug -3 in, I get a value of 2. Absolute value of 2 is 2. -1/2 times 2 is -1. And -1 plus 2 is, again, 1. So I'm going to go ahead and plot those points. All right. So the point -7 goes to 1. And the point -6 goes to 1.5. And then again, I take a look at this and I go, okay, -4 becomes 1.5. And then I have this -3, which makes a 1. Okay, so this is interesting because now I have a graph that, as opposed to going up, this graph is going down. And, you know, the question is why is that, right? So why is this thing going down as opposed to maybe possibly going up? Okay, let me run over that in blue here. So why is this graph in blue going down, whereas the original function was going up? And I suppose it has something to do with the value of this 1/2 here. So let's take a look at what we've got going on here, just to see, you know, if we can make a general rule. So before, notice the absolute value function, okay, it went over 1 and then up 1. It went over 2, up 2, over 3, it went up 3. Okay, so let's see what happens. Let's go back to this idea of moving over 1 like we always have, because I notice all of these points still are 1 unit away, but this time it doesn't move down 1, it actually moves down 1/2. So this value, see that negative? I think that negative has something to do with it going down. So let's check again, right? And then we go over 2, and normally we would go down 2, but now I go down 1. So that's interesting because normally if I went over 2, I'd go up 2, right? So normally I would go right 2, then up 2. Now I'm going over 2, but down 1. So what's interesting to me is that this 1/2 is important because I'm only moving half the distance of the original. So the negative, though, I think just simply tells me to go the opposite way. So if this had been positive, I think I just would have gone up as opposed to down, which ends up being the case. So if you have a negative, the negative does nothing for you other than it tells you to literally go the opposite way. So what happens is we call this a reflection. Okay, so when something is multiplied by a negative, it actually causes it to open the opposite way, which is called a reflection. So in this case, what I begin to notice is that this value that's directly out in front tells me how much to move, but it's based upon, again, this f of x that we had. So it seems to be really important that we know that the pattern of this f of x. So the absolute value of x, we need to know its relationship. That's going to be crucial and key to understanding all of these functions. So if I move left 1, right, I should also go up 1, but in this case, it's telling me to reverse that. So instead of going up, the negative tells me to go down. And instead of going 1, I get the half is also now telling me how much of the original to move. So as opposed to going left 1, then up 1, I'm going to go left 1, now down, and I'm going to go only half the amount. So half of the original amount of 1 ends up being a half. And look what happens here. So if I go left 1 and down half of the original amount, so normally I would go left 1 and down 1, the 1/2 is actually telling me to only go half of that distance, which puts me at a half increment value. So normally I would go left 2 and up 2, but the negative tells me to go down, so I'm going to go down, and I'm going to go half of 2, and half of 2 is 1, so I end up at my point, which is nice because it's mapping up here. So what this value, okay, that multiplier is doing, it's giving me direction to go for my output, and it's also telling me how much of the original amount to go. So this one said half that amount, and now it is a multiplication, so it's half of. So half times, so half of that amount. So I'm going to go and I'm going to multiply the original output by half. So I hope that's making sense, and we'll give another example and see what happens. Another example of this would be something like moving on to the next page. So let's, I'm going to have to set up the next page really quick, but then we'll go ahead and do it. Okay, so we have this new example, and this new example says h of x equals 3 times the absolute value of x plus 1 minus 5, and we're just going to continue with our hypothesis and make sure everything goes, and I might make a table in this case, or I might not make the table. The table's not necessary at this point. You kind of want to skip the table, but I'll demonstrate the table just to show and make sure that everything maps up. So remember we had before was positive 1. We ended up moving all of our points in unison the opposite of positive 1. So when I have a positive 1 here, my points actually move left. However, on the outside, they moved that direct value, and they moved in this one caused them to move up or down. So this caused my point to move left or right, and this one caused those points to move up or down. So in this case, I have positive 1, so I'm going to move it left 1, and this one here says negative 5, so I'm going to move down 5. So when I take a look at this one, right, what's important is, well, what am I moving and where am I moving from? You can actually take any point that you want that you know what's on the parent function, but I'm going to choose the most important one that we would call, which is basically called its vertex, where the two rays of the function actually meet, which is at 0, 0. So I'm going to start from 0, 0, where the original vertex is, and I'm going to move that, and I'm going to move it in blue. I'll stick with what I've been doing here. So I'm going to move this point to the left 1, and then down 5. And when I plot that point, I'm essentially using this almost like plotting a coordinate, except when I plot the coordinate, I'm just remembering that this is actually going negative 1, and that this is then going negative 5. So this one moves left negative 1, and then down to negative 5, and I plot my point. And now we also had something here that we learned that was interesting about this number that was out front. So this number out front was actually changing that when I didn't change how much I moved left or right, but this value did end up changing how much the function went up or down. And because it's positive this time, I'm going to presume that it's going to move me up. And last time it was negative and it moved me down. So I'm going to take this value of 3, and I'm going to keep in mind that if I went from the original function, okay, the original absolute value function, which went right 1, then up 1 to plot its next point, that I'm going to presume that this blue one goes right 1, and then it goes up 3. So over 1, and then up good old 3. So 1, 2, 3. And then I'm going to plot that point right there. So there's my point. And then I'm going to do the same thing. So if I go left, right, if I go left, it doesn't change anything, because if I go left, I still do the same thing as if I went right 1 value. So if I go left 1 value, I would go up 3. Now, if I went over 2, all right, just to remind you this, that if I went over 2 values from the original absolute value function, okay, I would end up going up 2. So this 3, I'm going to presume that it's going to say go up 3 times that amount. So because it's a multiplier, so I'm going to do 3 times that amount. So normally I would go over 2 and up 2, but instead of going up 2, I'm going to go up 3 times that amount. So 2 times 3 is 6. So I'm going to go ahead and plot that value. So over 2 and up 6. So to go from negative 5 up 6 puts me at the point of 1, 1 right here. And I'm just going to do the same thing. So I go over left and then up that same 6. And at this point, I believe I have enough points that I can just go ahead and graph this. So I'm just going to go ahead and graph this thing in here. Okay. And what I'm going to do here, just to double check, to make sure I'm not doing something wrong and my guess isn't wrong, all I'm going to do is I'm going to take a table and I'm going to plot the values of x in and just make sure that they actually create the values that I'm claiming them to create. So I'm going to use a table here. And I'm going to go x, and then just a quick little table, and go h of x. So the values that I've used so far are when x was negative 1, negative 2, and negative 3. So negative 3, negative 2, negative 1, and I also used then 0, and I also used the value of when x was 1. So basically, the points that I'm doing, I'm just taking the x coordinates from them, and I'm just going to make sure that when I plug them into the equation, all right, that indeed that I have kind of come up with a rule here that I can say that this multiplier out here moves the output, what we call, okay, in that multiplication amount. So let's plug in -3. So if I plug in -3, I'm going to do mental math on this one. So -3 plus 1, so the absolute value of -3 plus 1 is the absolute value of 2, -2, and the absolute value of -2 is 2. So 3 times 2 is 6, and 6 minus 5 is 1. Which is kind of cool, because when I just utilized this idea based off of how much the original function moved and I just multiplied it by 3, it actually, this 3, again, didn't change how much the x moved. It simply just changed how far up or down my coordinate then went. So in this case, I end up getting the point -3, 1, which matches directly to what I did when I utilized the numbers out of the equation. And if I plug -2 in, let's see, does -2 make an outcome of also -2? So the absolute value of -2 plus 1 is -1. So -1, absolute value of -1 is 1. So 3 times 1 is 3. And 3 minus 5 is -2. And wow, look at that. That's pretty cool. So when I plug the -2, I definitely get those points out. So it seems to be that I've developed kind of like a cool thing here, that what you got going on is that this value out front ends up changing how much you move the point away from the movement left or right. So if I keep the movement, the original movement of the function as going 1 to the right, this value right here seems to be just affecting the y value. And that's exactly what it does. And to give a name to this, all right, when that value out front, okay, ends up being a value, so we're just going to use a generic that you'll find is a, when that value, okay, of a, and we'll use absolute value because we're an absolute value function, when the absolute value of that function ends up being greater than 1, we end up calling this a vertical stretch. And that's a specific name to it, okay? It's called a vertical stretch. So what dictates the way it goes, if the vertical stretch goes up or down, will be the sign. So if it's negative, I stretch it down, and if it's positive, I stretch it up. But either way, it's called a vertical stretch. And the reason it's called a vertical stretch is because if I base it off of this vertex, all right, notice I move along the path of that vertex right or left every single time. So what that is called, it's called a fixed line. So that line I keep on resorting back to, and I keep moving 1 from this value. So I'm staying along this line every time. I move over 1, and then this time I went up 3. And this time I went over 2, and I went up 6. The original function would have gone over 1, up 1. So notice that when the multiplier out front was a larger number, it actually, when I went over 1, it moved my point farther away from this line. And because I'm moving it farther away from this line, that's where we get this idea of calling it a vertical stretch. So a stretch is a pulling away of something. And basically what happens is that this point is now being pulled away from this line down here, which is why it's called a vertical stretch, because I didn't change how much I went over. It literally just changed how much the point went away from this line. Okay, so that's vertical stretch. And what we noticed before was that when that value was, the absolute value of that a was less than 1, what you noticed was that it got closer. So remember when we did the 1/2 in the last video, or the last slide, when I went over a half, right? So when this multiplier out front was -1/2, okay, it went over 1 and then down 1/2. So in reference to the line, normally I would have gone up 1 full unit. Now I'm only going away from the line half a unit. So if I think about absolute value as this idea of distance, even though my number is below the line, it's still a closer distance. And because that value is actually making my point pull in closer to this fixed line that I keep moving 1 over or 2 over, okay, from this point here along this line, okay, the value when it was less than 1 ends up being what we call a vertical compression. And the reason it's called a compression, again, is because it's literally just moving closer to that fixed line along that vertex. So we had one other example that we started off with, and that was when the absolute value of a actually equaled 1. And when it actually equaled 1, so when there was no multiplier out front of the absolute value, we actually just stuck to the normal pattern. We went over 1, up 1, or over 2, up 2. Now, just remember, I didn't have an example of this, but if that value was negative out front, and it was just a negative, it doesn't have to have a 1 with it, you just have a negative sign out front, then remember that you would just change the direction that you would move up or down. You're not changing the direction left or right. So normally if you went over 1, up 1, if the value out in front is negative, okay, if the value out in front here is negative, we're just going to go over, and then we'll go down as opposed to going up. Okay, so I hope that helps with the idea of graphing these transformations, and I hope it all works out. If you have questions, let me know, and I hope this video wasn't too incredibly long, but if you liked it, give it a thumbs up, and let me know if you would like more on this type of video style. But have a good day.